Now it is time for a little implicit differentiation. Okay, don't forget that big fancy word differentiation. It's just the process of taking the derivative. So every time you see it, just remember, oh, you can take the derivative. That's all it really is identifying. It's a process of doing that. Now, what if I gave you an equation that looked like this? X squared plus y squared equals 36. Okay, now you may or may not remember that that's the equation of a circle. It is, and just for reference, I am going to draw us a little circle up here. That is a circle with an origin as its center, and if you remember from years past, we've discussed this equation in math analysis as well as geometry. This is r squared. So if r squared equals 36, that means that we have a radius of 6, which means it goes from plus or minus 6 to plus or minus 6. Okay, we're going to refer to that diagram shortly. Let's get back to our equation here. Now, if I asked you, take the derivative of this function, well, up to this point, the only thing you could do is get y by itself and then continue. So if you were to do that, you'd do this, right? You have 36, you'd move over the x squared, and then in order to get y by itself, don't forget your plus or minus. Now, even though that plus or minus might concern some of you, at least now you have a better plan of attack for taking the derivative, right? Y equals, this right here is explicitly stated for y in terms of x, okay? It is very clear what your function is. I have a function y, and it's clearly labeled that my variable is x inside that function. However, you can't always do that for an equation. If I'm asking you to take the derivative, well, what if the function looked like this? Let me just change the color here. What if I gave you a function that looked like this? Y cubed minus 2y squared equals 4x minus 9, or plus 9, it doesn't matter. As soon as you have something like this, getting y by itself is rather tricky, okay? Even if you had something like this, y equals sine of xy. Things like this exist. It's almost impossible, if not impossible, to get y by itself. So we have another plan of attack. It's called implicit differentiation. Okay, before I do our circle example, I do want to show you this simpler example first to get the idea. So say I gave you y equals 3x to the fourth. Now, short of the fact that you know the derivative is 12x cubed, let's think of this a little bit differently. Now, if I just told you to take the derivative of, if that were an x and I said to take the derivative, you would say, well, it's 1. Well, think of it the same way. If it's a y variable, you take the derivative of y, it's still going to become 1, except instead of taking the derivative of an x with respect to our independent variable, we took the derivative of y with respect to our independent variable. The independent variable is always on the bottom, and then what you're deriving is on top. Let's continue. Now, this is just when you do this, you get, well, you're going to get 12x cubed. Now, we took the derivative of an x term with respect to our independent variable. If you think of it this way, implicit differentiation should make sense. This is, anything over itself is 1. So if you're taking the derivative of x with respect to the independent variable, which is x, then it just becomes 1. And then 1 times anything is itself. Now, what I just did here was I made a easy problem hard. And it's only because I want to show you exactly what we're about to do now. Let's do this one now. Let's get back to x squared plus y squared equals 36. And we are going to implicitly differentiate. Let's do the first term, x squared. Well, it's exactly what you would think it would become. It becomes 2x, but because we took the derivative of x with respect to x, think of it, at least for now, we have a dx over dx. Let's continue with the next term. Y squared, well, it would follow the same pattern and it would become 2y, but we just took the derivative of y with respect to x. Include a dy dx. All constants become 0. 0 times anything is 0, so just make it 0. Now, this right here will happen every time you're taking the derivative of an x term. You don't need it because it's always going to become 1. So that will probably be the last time you see me write it. So when you're taking the derivative, when you're doing implicit differentiation, here's what you need to remember. Just take the derivative of x terms as if they're normal, and whenever you take the derivative of a y term, include dy dx. Now, remember what the derivative is. The derivative is dy dx equals, so why don't we just get dy dx by itself? I now have 2y dy dx. I move over the 2x. And then if I divide by 2y and divide by 2y, we're going to get ourselves dy dx all by itself. And this will simplify a little further. I can cancel out the 2's, and that's going to leave us with negative x over y. All right. So now, that right there is going to be the first type of questions they're going to ask you to find the derivative, but then you're also going to need to evaluate it at points. Well, what do I mean by that? Well, that's why I drew this circle. I mean, it's pretty sloppy, but let's pretend it looks like a real circle. Now, if I wanted to find the slope of the tangent line at this point, that would be the slope of the tangent line. I'm going to do two locations. I'm going to do these two locations for obvious reasons. This one is clearly vertical, which means it should have an undefined slope. And this one is horizontal, which means it should have a zero slope. All right, well, what are these points? This point right here is 6, 0, and this point right here is 0, 6. So let's see what happens. Here's our dy dx, and we want to evaluate it at 2 points. We're going to evaluate it at point 6, 0, and then we're going to find the derivative evaluated at 0, 6. That's the notation. And what you do is, well, now that our derivative looks like this is the first time we're going to be using x's and y's to find our derivative. All right, well, the negative x goes up top, which means it's a negative 6, and then the y value goes below, which in this case is a 0, and that makes sense because at that point, our slope is undefined. Let's try the other one. So now 0 is my x value, and 6 is my y value, and if you plug them in, well, that now equals 0, which is what we just said. Okay, let's do another example. Now let's take a look at this one now. And let's pick a pretty color. So I am going to take the derivative. We want to find dy dx, and we're going to leave it in terms of x and y. Well, we're going to do one term at a time. The first term is a y term, which means it becomes 1 dy dx. The next term is also a y term. So when you take the derivative, it becomes negative 2y dy dx. The next term is an x. If you take the derivative, it becomes 1. dx dx, we don't need it. I'm not going to put it. The next term, when you add it, you get 2x. And now here's our equal sign. Let's do the right side. That right side is a y value, a y term. So that's going to become negative 6y squared. Don't forget dy dx. All right, now unlike the one we just did, this one has 3 terms that have a dy dx with it. How do you get dy dx by itself? The trick, well, there's a few ways of doing it, but this trick seems to work for most people. Let's get all the dy dx's on one side. Since I have 2 on the left, I'll keep these 2 here, and I'll move that other dy dx over to the left. That means this is going to become a positive 6y squared dy dx. And if I'm going to move all of them to the left, let's move over the other ones to the right. So that would become a negative 1 and a negative 2x. Okay. Let me just take a quick look. Did I do it right? Positive 6y squared. Good. All right, now here is what we want to do. These 3 terms here have a common factor. They may have more than just a dy dx in common, but we're trying to solve for dy dx. Take out just dy dx and watch what happens. I'm left with a 1, a minus 2y, and a plus 6y squared. And that right there, my friends, is the trick to getting dy dx all by itself. Because now if you want to get rid of what you're multiplying it by, just divide by what you want to get rid of. And what you do to one side, I think you remember you do to both. That cancels with that, and here is dy dx. It's that fraction right there. Now this implicit differentiation problem is a little trickier. If you notice, we have a 3xy cubed. Now this term right here, because we have 2 different variables, right? You can think of this as a 3x times a y cubed. We must use the product rule there. Okay, so we're going to use the product rule there. Watch how we do this. The first term, it becomes negative 1 dy dx. Negative 4x. Now for this one, we have to use the product rule. This is going to be my f function, and this is going to be my g function. So the derivative of f is 3, leave the second, plus I'm going to leave the 3x, and I take the derivative of the next term, which is 3y squared, We just took the derivative of a y term. We need dy dx. All right, so let's just clean this up a little bit. I have a -1, we have dy dx. And there's not much more we can do here except, what does this thing come out to be? This is just going to be a 9xy squared dy dx. Well, after that, everything else is pretty much the same. Our goal is to get the two dy dx terms on the same side. So that would be, I have a -1 dy dx and a -9xy squared dy dx. And we're going to leave these two terms right where they are because they do not have dy dx's. And what is that going to do for us? Well, now we take out the common factor. And that's going to leave you with a -1 minus this. And you divide by what you want to get rid of. And that right there is dy dx for this problem. I say one more example using the product rule is a wise idea. Let's make sure you understand this. The first term is a y term. That's going to become 4y dy dx. Now for this term right here, this one I'll do in blue. The negative confuses a lot of people, so just do this. I'm going to add, well, what's the next thing? Well, the next thing is going to be this -x is my f times this y, which would be my g. So now the derivative of the first is -1, leave the second, plus leave the first one, and take the derivative of y, which is 1, dy dx. The next term right here is a constant, that becomes 0, and this term right here is an x term, it becomes 3x squared. We do not need the dx over dx. The last term on the right here, that's a 0, that's a constant. Constants become 0. All right, let's clean this up. We have a dy dx term right here and right here. Those are going to keep where they are, and then this term and this term will move over to the other side. On the left, we have a 4y dy dx, and this becomes -x dy dx. Over on the other side, well, this is a -y, right? -1 times y, so that'll become a positive y, and then a -3x squared after you move that one over. Our next step is to take this common factor here, remove it, and after we take it out, we have a 4y minus an x left in there, and over here we have this. Oops, I meant to write y minus x, and then over here, 4y minus x. There is our derivative, dy dx, dy over dx equals that.